Hello class, and welcome to week 12 of our online lecture. This is the last week that we're covering bivariate associations. This is the last component assessing associations between two variables. Okay. This week we are going to learn how to generate means by groups using a t-test and an ANOVA. Okay. Now, just to recap what we've covered thus far, week 10 we covered bivariate associations correlations, where we are able to assess the relationship between two continuous level variables. The Pearson R correlation coefficient tells us about the direction and the strength of the correlation between those two variables. Okay. Week 11, we covered cross tabulations and chi-square. Cross tabulations are used to assess categorical measures using contingency tables. And the chi-square value is the test that indicates whether or not the differences seen in the categories of those groups is statistically significant, meaning that those effects are not just occurring by chance. So this final week, we are covering means by groups, which are very different assessments than anything we've covered up until now. Okay, we're going to start with the t-test. Okay, we're going to cover the independent t-test only. There are several types of t-tests. We are only going to cover the independent t-test. Now, what is a t-test used for? A t-test allows us to compare the averages or the means of two independent groups. Okay, when we say independent groups, we are referring to the variables categories, which indicate groups different from each other, or there are different people in each group. So what the t-test does is it analyzes both variables and it looks at the averages by each group. So remember, when we were learning variable levels, the levels of measurement early on in the semester, we were talking about how one of the important and most noticeable components of a continuous variable is that you can generate a statistic of a mean or an average. Okay, that is the only type of variable that you can generate an average for. So if a t-test is designed to look at the means of a variable, well, that should tell you right off the bat that one of your variables has to be continuous. And if we are assessing the averages by group, that tells you that the other variable has to be categorical. So the independent samples t-test, which is what we're covering, this is the most common of all t-tests used when you are looking at two separate samples. Okay, when we don't have information on the general population mean, okay, the average across the population, or we don't have any information on the standard deviation, using the independent samples t-test is best, because this type of test doesn't require that kind of information. Okay, it does require that you have two independent and separate samples, meaning that your categorical measure has two categories. Here's an example. We can run an independent t-test if we want it to look at the average test score. And by test score, think about the LSAT or the GRE or the SAT. So we want to assess the average test score of males and females, and we want to see if those average test scores are different. So when we run the test and it produces results, this is going to indicate whether or not the differences that we see in the average test score by group is occurring by chance, okay, or if it's a legitimate difference, a statistically significant difference. Okay, now when we run a t-test on SPSS, SPSS is going to spit out standard output, okay, with information inside a box labeled the Levine's test. The Levine's test is just one of the standard tests that we use to do the calculations for the t-test. Now, the coefficient under the Levine's test tells us about the relationship. Okay, so if we look at this coefficient for this test and it is statistically significant, that tells us something. That tells us that the differences that we observe in the test scores by gender or by sex are significant and they are not occurring by chance. All right, so that's a quick run through of the t-test. Here is information on the other types of t-tests, which again, we will not be covering in this class, but feel free to look it up if you're curious. Okay. Now this second part is going to cover the analysis of variance, also called the Anova. Okay, this is another type of test that allows us to look at averages by groups. Now, this is really simple, and I want you to think of it this way. The Anova is basically an extension of the t-test. Okay, so remember that the t-test is comparing an average, but it's only comparing an average for two groups. That's all a t-test allows you to do. A t-test allows you to look at an average of whatever variable by two different groups, and that's it, meaning you can only use a binary variable or a dichotomous variable in a t-test. Okay, however, an Anova does a similar thing, so it detects differences in averages, but it's able to look at those differences in the averages for three or more independent groups. This means that we can use categorical measures with more than two categories in an Anova, and we can test the average level of whatever we're looking at across those groups within the categorical measure. Okay, so again, just like the t-test, an Anova requires one continuous level variable, again because we are computing averages, and then one categorical variable, but this time it has to have more than two categories. What the Anova does in the background is it sort of calculates a ratio of the levels that happen between groups and then within groups. And that calculation allows the Anova to indicate whether or not there are statistically significant differences between the groups or not. Okay. Here's an example of when we can use an Anova. If we want to assess the average income across racial and ethnic groups, Anova is a perfect test. Okay, so if we recall in the GSS, the race variable has, I believe, 3 categories: whites, blacks, and others. So we would be able to run an Anova looking at a continuous outcome across race. Okay, and similar to the t-test, the Anova is going to tell us whether or not the differences in income across these racial groups could have occurred by chance or if there is a real underlying mechanism occurring relating those variables together. When we perform the ANOVA, it is going to have an output similar to the t-test, and it's going to produce an f-test. The F coefficient is what we are concerned with for the ANOVA. If this coefficient has a significance value that indicates significance, what we are able to deduce then is that there is a significant difference between at least one pair of averages. Okay, so I'm going to move on to the SPSS component up for this week. Okay, so go ahead and open up your syntax file and notate week 12. Again, we are going over bivariate associations, means by group, t-test, and ANOVA. I'm also going to show you how to produce a simple means table that lets us look at the average level of our continuous measure by whatever group we are specifying. So we can calculate very basic descriptives with the means table command equals one continuous measure, so whatever continuous measure you choose, I'm choosing age, by whatever type of categorical measure. It can be dichotomous or it can have two or more categories. I am using the variable pres19, which is asking respondents if they voted for Hillary Clinton or Donald Trump. This cells line, be sure to specify mean, count, standard deviation, min, and max. If we highlight this and run the code, this is the output that we see. We get a simple case processing summary, which tells us the number of respondents who responded to both questions. And then down here, we see the report. Okay, this is just a basic means table. So this is telling us the average age of respondents who voted for Clinton and the average age of those who voted for Trump. Okay, so we can see here that the average respondent who voted for Trump is several years older than the average respondent who voted for Clinton. So the average age for Trump is about 57 years old. The average age for Clinton is about 52 years old. And we can see here the number of respondents who responded yes to either one of those names. Okay, so this is just a very simple report that gives you really meaningful information. Let's go ahead and do another one. I'm going to run a similar table looking at income by, again, this President 16 variable. So this table is going to allow us to see what the average income of respondents were selecting either Trump or Clinton as their presidential candidate. Okay, we can right off the bat see that those individuals who voted for Trump have a significantly higher average of income than those who voted for Clinton. So Trump voters average about $43,000 a year, while the average Clinton supporter has an average income of about $35,000. Okay, very interesting results. And again, you can, I think honestly this is one of the most interesting and funnest syntax to run on SPSS, because you're able to kind of pick and choose what variables you want to assess for good reasons. Okay, so the last means table I want to run is this one here. I want to look at the average reports of sex frequency, so how frequent a respondent reports having sex by the person's marital status. Okay, now statistics from national surveys continually show that despite what we might anticipate, those people who have more sex than anyone else are those who are married. Okay, everyone thinks that single people have more sex than everyone else, but that's not true. So if we were to run this command, this is the output that we see. And the results reflect those national surveys that are conducted in this area. We can see that married individuals have a much higher average of sex frequency than any other group. The lowest average are among individuals who are widowed. Okay. Following married individuals, people who have never been married have the second highest frequency of sex. So this is some interesting stuff. All right, so that covers basic means tables. Now let's move on to running t-tests. Okay, again, remember, a t-test, we are looking at the average of a continuous variable by a categorical measure with only two categories. So the code here is t-test groups equals the name of the variable, and then in the parentheses you want to specify the values of both categories. So if we were to run a code book for sex, we would see that 1 is labeled male and 2 is labeled female. So we are just denoting that for the t-test. Missing equals analysis. Variables equals mental health, which is the continuous measure. Again, this is the variable assessing days of poor mental health in the last month. And the final line, we want to set a criteria with a confidence interval of 0.95. Don't worry too much about that. That's something that you will learn in a more advanced statistics class. Let's go ahead and run that. Okay, again, we get a preliminary window. This is the group statistics. So here we can see the results for the average days of poor mental health by sex. Okay, so if we look at the means here, we can see that females report more days of poor mental health than men do. Men average about 2.8 days out of the month. Females report about 4 days out of the month. Now, the whole point of a t-test is to say, okay, well, we see that there are differences in mental health outcomes by gender, but how do we know that this relationship is real? How do we know that this is not just a data thing? How do we know that this is not just occurring by chance? Well, that's what this independent samples test does. Okay, so this box down here runs a test on this relationship. Okay, now this is the F value that I told you. This is the F value that tells us about the t-test. And right next to it is the corresponding level of significance. So what we see here is the independent samples t-test has a coefficient that is statistically significant, and it is very significant. It is significant at the 0.001 level. So what this means is that the differences that we see here in mental health are not occurring by chance, that there is something underlying this phenomenon that is creating this effect. Okay, let's go ahead and run another t-test. Again, I want to specify the two category variable here. I'm going to use the president variable again with 1 and 2, Clinton and Trump. Response categories, same code after that. Let's run this. So we are looking at how often respondents pray, and it's looking at frequency, and it goes from never to several times a year, several times a month, once a week, all the way up to level 8 or 9. So if we look at the mean here, we can see that Trump voters have higher averages of prayer than Clinton voters. It's not by much, so the Trump supporters are averaging somewhere between 7 and 8, which is like once a week and more than once a day. And Clinton supporters are averaging right at around 7. So the next part is to look at the actual t-test output. Again, here is the F coefficient for the t-test, and here is a significance value. Again, this relationship is statistically significant at the 0.001 level, which means that the differences in prayer across Clinton and Trump supporters is statistically significant, and this effect is not occurring by chance. All right. Lastly, let's go ahead and cover the syntax to run an ANOVA. Again, remember the ANOVA is just like the t-test, except you can assess a categorical measure with more than 2 categories. Okay. The code for that is one way. Then you want to put your continuous measure first by your categorical measure. Okay, so I'm looking at the average level of education by religious denomination. Statistics, descriptives. Last line is indicating missing values. Let's run this command. The first output window you're going to see is this descriptives. Okay, it is basically just giving you an outline of the total number of respondents per category, and then it gives you the average of your outcome variable. So this mean is the average level of education by religious denomination. So let's see, who has the highest income? That would be those who identify as a religious other, averaging at about 15 years of education. That's followed by people of no religion, followed by Protestants, then followed by Catholics. Now, we can see that there are differences in education by religious denomination, but are these differences statistically significant? To answer that question, you go down to the Anova window. Okay. I want you to look straight to the end columns of the output. Again, we have the F statistic, which is just the statistic representing the ANOVA test. And then we have its level of significance. Again, we have a very significant relationship between education and religious denomination. So the differences that we see across denomination are not occurring by chance. Okay. Let's see. Let's do one more. Let's do one more ANOVA. Let's look at number of children by religious denomination. Okay. Here is the average number of children by denomination. So the denomination that averages with the highest number of children is Protestant. That doesn't surprise me, since they tend to abide by traditional family values and tend to retain very conservative values when it comes to family and the home. So this is not surprising that they average the highest. This is followed by Catholics, religious others, and then, not surprising, is those with no religion average the least amount of children. Okay. Now, are these differences in number of children significant? We go to the F value and its significance level. Yes, the relationship between denomination and number of children is statistically significant at the 0.001 level. So the differences we observe here are not occurring by chance. Okay, you guys, that concludes our lessons for bivariate associations. Week 13 and 14, believe it or not, we are going to cover regression analysis. So we are getting into the hardcore stuff that I had talked to you about at the beginning of the semester, and now we have arrived. So go ahead and make sure you read your book on regression, simple regression, and multiple regression, and I will talk to you all next week. See you later.